Okay, so our tutorial today will be our practical today, sorry, will be beam deflections calculations. Okay, today we will have two cases of beam deflection need to study. The first case is concentrated loop. Okay, sorry. So the first case today is the concentrated load B, and the second case we have is uniform distributed load. Okay, these two loads will be applied on simple beam. So we will study only today simple beams with a span L, and the applied load will be the first case concentrated load B at the middle of the beam or at the mid span of the beam B. This B is here at mid span. Okay, and the second case we have is same beam, simple beam, but the load will be uniformly distributed, and this load we can call it Q small or W small over a span L. Okay. Last week we know the formula and the maximum deflection for these two cases. The maximum deflection or the deflected shear first will be something like this, and the maximum deflection will be in the middle, delta. The value of delta is given using the or calculated using the formula B L to the power 3 divided by 48 EI.
So does that say PL cubed?
Yeah, BL cubed divided by 48 EI. Okay?
EI.
This is the formula for the deflection for concentrated load case. For the uniform distributed load case, also the maximum deflection will be at the mid span, and the maximum deflection here is called delta, and we can find the delta using the formula delta equal to 5 multiplied by W L to the power 4 divided by 38 384 EI. Okay, this is the formula for uniform load, and this is the formula for concentrated load. Okay, and as we know before, B is the load, applied load. L is the span of the beam. E is the material properties of the beam, which is Young modulus, probability of beam of material, because this beam may be from steel, from aluminium, from wood, anything. So E is the Young modulus of the material. I is the inertia of the cross section of the beam. Okay, so if we know all this parameter, we can calculate the deflection delta. Here for the uniform distributed load case, 5 divided by 38, this is constant of the formula. W is the uniform load, uniform distributed load. L again is the span. E is material properties Young modulus. And I is the inertia. Okay, these formulas is theoretical. You can put it here, theoretical values of the deflection. Our rule today or our tutorial today is to compare the experimental results with the theoretical result to see the difference of the accuracy of the formula. Okay, so we will do these two cases for our test today or our experimental work today. Okay, so today we will have these two cases in the experimental work. The first case is the simple beam to compare with the formula with the concentrated load B. Okay. But here the section of the beam, we have 5 types of beam today. If you cut here in the beam, we will have 5 cases or 5 cross sections. The first section is the solid rectangular or solid bar rectangular shape section. The second section is square hollow section, SHS. The third section is rectangular hollow section, RHS. The fourth section is circular hollow section, CHS. And the final section is C section or channel section. So we will repeat the test 5 times to calculate or measure the dimension, the deflection for each case. Okay. The shape of each beam, what will affect us? What will this affect us? This will affect us in the equation, because if we return back to the equation, delta is equal to P.
Yeah.
Yes, I am recording now and I will upload this for you again. Okay. So this delta equal to, as we said in the previous slide, BL to the power 3 divided by 48 ER. Okay. So for this is the formula. For our test, we are comparing these 5 shapes together. B is constant or similar in the 5 cases, so this is not a parameter to compare. L also is, we have same length, so is not a parameter to compare. E, all this material or these shapes are from aluminium, or the 5 beams are from aluminium. And E is given for aluminium, E equal to 70,000 MPa. So the material for all beams are same. The only parameter we will study is the effect of the inertia or the shape. So we have 5 I's, I for case A, I for case B, I for case C, and I for case D, and I for case E. Okay, so we will find the inertia for these 5 beams or 5 shapes, and then calculating I for each one, then measure or calculate the deflection delta. Okay, how to find the inertia To find the inertia or to calculate the inertia, we need to know the dimension for each shape. If this tutorial or this practical was in the lab, you will measure the dimension of this shapes. Okay, so you know this is the width b, and this is the thickness or the height t. Here as well, you can this square. So this b, if this b, so this is b, and you can find the thickness t. Okay, this the width is b, and the height is h, or and the thickness is t. Okay, because if you know the outer dimension and the thickness, so you can find the inner dimension. Okay, also here, if you know the outer diameter d and the thickness t, so you can find the inner dimension. Here as well, we need to know b, and this is h, and the thickness is t. So in the lab, using the vernier capillary, you can measure all these dimensions, so you can find the inertia for all beams. And using the inertia for all beams, you can calculate the deflection for them. Okay, we will repeat this 5 cases or this 5 cross section shapes in the second case, which is the uniform distributed load. So if we have uniform distributed load W and the span L, we will have same 5 cases. A is the solid bar or the rectangular bar. B is the square hollow section. C is the rectangular hollow section. And D is the circular section. Okay. So, and E is the channel section. Okay. This 5 section is similar to this 5 section, so same dimension. If we apply the equation here of deflection, delta is 5 W L to the power 4 divided by 384 EI. This is the deflection formula. And again, for this case, W is not a variable or not changing. L also is not changing because they have all same lengths. E also is not changing because all from aluminium. So E equal to 70,000 MBA. And I is the only variable we are studying here because we will have IA and IB, IC, ID, IE. So we will calculate the deflection for the 5 beams and compare between them. Okay. So this is generally the idea of our practical, is to test 2 cases of loading with 5 shapes of cross section for each case. So this is about 10 cases of testing if you are doing it in the lab. Okay. Now I will shift to the project or the practical description to explain how we will do the practical if we are doing it in the lab. Okay, can you see the setup? Okay, this setup is the setup for the test. This is available in building, and it is very simple. We are just laying the beam horizontally over two supports. This is the two supports, as you can see. And then at the middle, we will put a dial gauge or LVDT to measure the deflection. And we will apply the loading if this concentrated load. So we'll apply the load at the middle and then record the reading from the dial gauge. So applying load and then record the reading. Okay, so this is how to do the deflection testing or to measure the deflection at the lab. Then using these measurements, we'll compare it to the values from the formulas. Okay, as you can see, the beam in the setup is the horizontal or the RHS section, rectangular hollow section, and you will repeat this with the circular hollow section with the channel and see the difference of the difference between them. Okay, so I will return back again to the bench to explain to you. I will again explain the setup. So in the experimental work or the experimental study here, we will have the first case is the load B or the concentrated load B. Here in this setup, the beam will be lying horizontally like this over two supports. This is first support, and support in the other end. These two supports are presenting the ruler and hinge. The distance between the two supports is our span L. And given for you in the, if you measure the dimension of the beams, all of them will be 900 millimeter, just to be comparable to each other. All of them with the same length. Okay. Then at the middle, here at the middle, or at the mid span, you should set up your dial gauge, and you need to re-zero it each time to record the deflection. Okay, this dial gauge will be here because you expect the deflection at mid span, so this dial gauge should be at mid span, L divided by 2, L divided by 2. Okay. The last thing we need to know is how to apply the load B. If you want to the lab, if you go to the lab, you will find that they are providing some small weights. Each one of them is 5 Newton, and you will have 10 of them for each group. So we have 10 weights. Each weight is 5 Newton. So the maximum weight we have, or the maximum force we have, is 50 Newton. We will apply this 50 Newton to the beam, but gradually, to measure the deflection at different level of loads. So the first point, or the first case, we will put this 5 Newton here at the middle and record the deflection. Then add the second one and measure at 10 Newton. Then the third one to measure at 15, and so on until we reach 50 Newton. Okay, so this is how to apply the concentrated load. So you will have like levels of loading and corresponding level of deflection. And if you want to record this, you can make this in small table for the experimental work only. We have the load, and we have the deflection reading or the deflection measurement from the experimental work. Okay, so if the load is 0, there is no deflection, so the deflection is 0. First step is adding the first 5 Newton and record the measurement. We can say 0.1 millimeter. Then at 10 Newton, the reading is 0.2 millimeter, and so on until reaching 50 Newton. Okay. So at 50 Newton, let's say 0.5 millimeter or 0.6 millimeter, whatever. So this is the deflection reading for the first case, the horizontal or the concentrated load B. Okay. And you need to repeat this testing for each cross section. This first case, let's say this was the solid bar. Then the second case is the square hollow section. Then third case, and so on. RHS and so on. Okay, so same procedure, but only changing the beam, and the only parameter changing is the shape of the beam. Okay, this is the first case, the concentrated load. Okay, the
Yep.
second case.
Yep.
Okay. Do you have any question? Anybody have any question?
That's pretty straightforward.
Okay, good. So now we will go to the second case is the uniform load. How to apply the uniform load for this test? On this test, here the beam is again lying horizontally. Okay, over two supports again. The span, again, you should set up the span to be L equal to 900 millimeter. And we expect that the maximum deflection will be in the middle of the beam. So this is our dial gauge here. And we need to re-zero it each time. This dial gauge is located here at L divided by 2, L divided by 2. Okay, and again, as we said in the concentrated load, we have 10 weights, each weight equal to 5 Newton. So the maximum load we have is 50 Newton. But here we are not applying the load at only one point. We need to distribute the load. How can we distribute the load? We will just distribute the weights over the length. Just put them beside each other to spread the load over the length. Okay. And the width of the load is calculated to nearly distributed over the beam. Okay, so each one of them is 5 Newton, and we have 10 of them. So how can we find the value of W, or the magnitude of W? W here is the uniform distributed load. To find this value, we have 10 weights. Each weight is 5 Newton. So this is the equivalent concentrated load. And we distribute this over the length, which is 900 L. So L, okay, or I will write it here. Because the value of W is not given, so you need to know it yourself. So W will be the magnitude of the load divided by the length. Okay, so this gives you, I will calculate the value for you. 50 by 900 give us a value 0.055 Newton per millimeter. Okay, so this is the value of the load we need in calculations. Okay, here in this case we cannot apply the load gradually because we have because it is distributed load, so we will have only one value for the deflection here. So the load W, let's say 0.055 Newton per millimeter. The corresponding deflection will be, let's say, 0.7 or 0.5, whatever millimeter. So here we have only one value, not gradual or not many levels of load because we don't have more weight, so we need to add the load at one time. Okay, this is the testing and how we can do the test. And if we return back to the project setup, a project description, here you will find this explanation again. And here in this page, you will find this is you need to do this report or filling this table to submit your report. Here you will find the dimension for each beam. This is the flat bar or the solid bar. You will find table with different level of load from 0 to 50 as we said. And here is the gauge length, or we can gauge reading. We can say this is the experimental results we have. And you can find here we have another column which is the predicted deflection formula. How can we fill this predicted deflection formula? Do you have any idea how to do this? Okay, this is to apply or to compare with the formula we have, delta equal to B L to the power 3 divided by 48 EI, right? This is just to compare, but we will not compare the maximum deflection only. We will compare at each level of load. So here, you know, L is given as 900 millimeter. E is given to you as we said aluminium, so E will be 70,000 MPa. And here I is you have calculated inertia for each beam. So what you will do is just you have this B. So you need to using Excel or using calculator put B equal to 0 and get the corresponding deflection. B is 5, get the corresponding deflection. B is 10 and get the corresponding deflection until 50. So you get the maximum deflection. Okay. So the predicted formula column, we can fill this with using the formula for the deflection. Okay. And if we have a look here, you will find that at the end of the table, we have uniform distributed load, but we have only one row for this value, for this term or this parameter. Why? Because we are applying the uniform load at once. We are not applying it gradually, so we have only one value. So you will put the load 0.055, the gauge reading as you measure from the gauge dial gauge, and how to find the predicted deflection formula. To find this value, we need to substitute in the formula 5 divided by 38, 384, WL to the power 4 divided by EI. Okay, so here we know W as we calculate now 0.055. L is the span and it's given 900 or you measure it 900 millimeter. E is the Young modulus for aluminium, 70,000. And I is the inertia for the beam, and you already calculated. So you can fill the table using these two formulas. The first formula, delta equal to BL to the power 3 divided by 48 EI, and the second formula for uniform load 5 WL to the power 4 divided by 384 EI. Okay? And you will repeat this calculation for the remaining section. Okay? Do you have any questions
No questions.
regarding this? Okay, all good with the practical?
Yep.
Yeah. What your role now is just to watch the video online, and you can record the measurement from the video, and I will be here to answer your question if any.
Okay.
And your final report, also you will find here how to submit the final report. But the main part is to fill this table using the measurements, and you need to, if you want, you can do this graph. This graph is just a comparison between the measured deflections and the predicted deflection. Okay, using this table. If you have a look on this table,
Yeah.
sorry, I will return back to the. If you have a look on this table, you can draw a relation or the graph between the load and the gauge reading, and the load and the deflection, the predicted deflection. Okay,
Mm-hmm.
but this is not the main thing. The main thing is to fill the the table first. Then, if you're happy, you can do this relation. Okay.
Yep. Where do you find the video on Learn Online?
You cannot find it.
No.
Okay, just a minute. I will try to find it for you. It is not in the video resources.
I don't know where it is.
Okay, well, try to find it for you.
Okay, using Panopto for the first time. The way to access it is to go to, once you click all folders, you go down and get started with Panopto folder. And you can find a whole heap of videos in here on editing, uploading video, automated recording. I won't go through all of them, obviously.